Hello. Hello. Good afternoon, learners, and welcome to this live session. Please say hello on the chat if you're tuned in and listening. Good afternoon. I hope you can hear me. If anybody has tuned in to see this live session? Yeah. Hi, Arnab. Okay. Thank you, Arnab. Anybody else? Because I'm going to solve some problems today, so somebody has to be there to see the and ask me the questions. Good afternoon, Subramanian. Okay, those of you who have logged in, Arnab, Subramanian, do you have any questions? What do you want me to, any requests of what I should do in this session? Good afternoon, Nalini. Yeah, whoever is joining, you can even just add whatever you, what is it that you want me to do today? Right? You have to say, you have to be a little participative in these live sessions. Otherwise, me speaking, you have already seen all my recorded videos, I am only speaking. So I know I cannot see you or hear you by your voice, but if you write text and say what is on your mind, then it will feel like an interactive session. Okay. Yeah, Subramaniam. Okay. Okay, let me check the form. Checked it from back. You can just go ahead and ask it now if you want. Okay. Key highlights, summary points of what? Okay, I can see the question. Can you run through quick highlights, key summary on this subject? Any other points that you would like to mention besides mentioned in the weekly course? Okay. That's the only question I have gotten in the form. So I think I had actually in my last lecture, I have summarized some things, and maybe those are the main things for me to summarize. I would what I would encourage everybody to do is that look at this course as really a mathematical theory to verify your experiments. The kind, if you are in this space, if you are doing any kind of experiments where there is somewhere there is some queuing happening, somewhere there is some resource that multiple users are using in many ways. We gave so many examples, right? Very first week, I taught you how to think of anything as as the generalized that which is in its generalized way a resource and a queue. So if you have a resource and a queue in your system, try to use queuing systems theory for it. That's the key highlight. If you were to forget everything else, still try to remember Little's law, still try to remember MG1, try to remember the single queue closed system. All these things are useful, and that's, I would say, the key highlights. Maybe the mean value analysis, last week gets a little difficult. You can, maybe that's not something you'll remember that easily, but do remember, remember laws of tandem queuing networks. Those are very important. That is very similar to pipelining. So those are the highlights I would say that you should try and remember. At least you should, I don't mean you should remember the formulae. You should remember that, yeah, there is, this looks like a standard single server queuing system, or it looks like a GGCK queue. I know where to look for formulas for this system. I'm going to go and look at those references again, and I will find those formulae. So GGCK and a closed say simple closed system, those are extremely important. Like, if you just remember those, it can help you in a lot of advanced work in your professional life also. Whenever you take up a job, if you're not doing only coding, if you're doing some experiments and performance work, this will really help you. Okay. Yeah, any other points that I would like to mention in the session? Really, in fact, the whole point of the course was to not expand things too much. There is a very minimum amount of theory that is good for people to know. Therefore, this was actually a big course. It's a 12-week course in IIT, and I kept removing things to actually just the essential, and made it so that it is into 4 weeks. So you can say a lot of things. I mean, if you have any specific questions, I can say, but that's not much. I mean, one thing I can say is that um, in the future, I might make the expanded form of this course, and two other uh, methods that I didn't talk about much in this queuing systems course was, one is using discrete event simulation. That is a very powerful method to do performance analysis, and it involves coding. So if anybody, I might actually give another sort of short 4-week course on it. Maybe that's something you can look out for. Or if you want to learn about it yourself, then there is a book called Law and Kelton. I might write it here. Law and Kelton Simulation Modeling. It is also very exciting. Simulation modeling is a lot of fun. It is a very powerful method to do performance analysis. So that's something you can look into. And the final thing is, nowadays a lot of machine learning is being used for performance analysis, because you can just generate a lot of experimental data and then just use machine learning methods which are very data driven. So we are looking into that also. In the course that I'm teaching at IIT, the last 3-4 weeks nowadays, we are looking at machine learning models. Frankly speaking, it is not my favorite method of modeling systems. I think when you do machine learning, you choose to ignore to study how things work. Whereas in queuing systems, it is so very beautiful. You're really trying to understand how something works and model it based on your understanding. Machine learning means you want to model something without understanding it. And it's not my preferred way, but it's just a trend. If a system is very complicated, it is very difficult to understand that system, then you may want to treat it as a black box and just do a data driven model. So these are sort of the frontiers nowadays of performance engineering, performance analysis. There is a lot of machine learning going on there, and again, There are some papers we can share. Subramanian is asking, as current direction of software products are in cloud, already anything related to queuing systems might vary or still holds good? It's a very good question. Yes, the queuing systems models become complicated because, I mean, if you think of a GGCK queue now, I hope you understand all of these terminologies. So in cloud, what will happen? The C stands for number of servers, right? The C itself might vary over time. So it's elastic. Maybe the cloud is adding servers, removing servers based on your need. In that case, it becomes a little complicated. At the same time, if you are getting fixed resources, then queuing systems model still applies. And many cases, just because it's on the cloud doesn't mean you're getting elastic service, doesn't mean you're getting dynamic resources. You will still sign up for some fixed number of resources, and you can still for your initial capacity planning and your initial estimates, queuing systems will still solve about 80% of your problems. It is surprising how much it will solve for you. You should not give up. You should first try to use queuing systems. It's like the basic things. You might say, just because something requires integration and derivatives, does that mean you don't need, simple addition multiplication? That is never the case. The basics will apply to some extent, and then when they don't apply, you give it up and say, okay, this is too complicated. Queuing systems will not apply. But never give up in the beginning. Always try. Always see whether simple queuing model will help you do some estimates and so on in the beginning. Okay. I will, if there are no more questions, I would like though from the students, okay, from the learners, which questions do you want me to solve? That tells me also that you have invested some time thinking about which question you want me to solve. I will just pick something random and solve, that's okay. You can tell me what question you want me to solve, out of which assignment, which question would you like me to solve? And don't be afraid. Just tell me which question. It's not even in the form. Nobody has put any questions to be solved in the form. I have one person who keeps asking about some assignment questions on the discussion forum. I don't know if he has logged in. Looks like he hasn't. So why should I solve what he's asking? I want to solve what what you want me to solve. Any tips for the exam? Just the assignment questions. I have not. I mean, this is really. I'm just going to go ahead and tell you. I have not. I'm not asking open questions out of the assignment format. This subject is difficult enough. So if you just do the assignment problems, uh, pretty much the format is the same. Similar questions, different numbers, that kind of thing. So solve the assignment. That's the main tip. Okay, assignment 3, which questions? Let me bring it up. I'll just share my screen. Oh, sorry, not this. Huh? This SWAM course is visible, right? This is the student view. This is the assignment. Okay, there is one more question. This course mainly focuses on the performance evaluations of the various key models. So we will also learn some performance parameters of transient solution approach. What do you mean transient solution? Do you mean time dependent? That is very advanced stuff. I don't do that. Like performance as a function of time. If that's what you mean, Manish, we have not dealt with that at all in this course. In 4 weeks, it's impossible. I don't even do it in the entire course in my IIT course. Even in one whole semester, we don't do transient modeling. We'll also learn some, no, you won't. No, you have learned what you've learned now, everything is open, right? So 4 weeks, I think all the lectures are released, right? And I'm not doing anything in transient. Everything we do is steady state. Everywhere we assume that the system has achieved steady state and it's not changing probabilistically anymore. So I think steady state was explained in one of the earlier lectures. If you would ask me a follow-up, then I can be more clear. I'm not very sure what you mean. In queuing systems and stochastic processes, transient solution means when you're trying to answer the same questions like what is the, let's say, queue length, right? We are only talking about queue length in steady state. And we are only talking about averages. We didn't even talk about distributions. So what is the average queue length of this server, after the server has been warmed up for some time? That is what we are answering. But advanced question, we can also say that, okay, system has just started, server has just started. What will be the expected queue length, 20 milliseconds after the server has started. So 20 milliseconds after the server has started, server will not have warmed up. Or 3 seconds after the server has started, maybe the server would not have warmed up. So it's not in steady state. And this is called transient analysis in stochastic processes. That is very advanced stuff. I don't even do it in the entire course here. It is very interesting work. I can do it. I did it for my PhD and all of that, but it is more like PhD and all of that level stuff. If you're interested, it'll be great. You should pursue it. Masters or PhD or something like that. Okay. Okay. I will go to, so out of this assignment, what do you want me to do? Question 4 to 6? Question 7 to 10? All these? Maybe not the first few questions, right? Or should I do the whole assignment? What do you want me to do? Yeah, these answers are okay. I think this you can figure out. I'll do question 4 to 6. Okay, you guys have to say something. Nalini, you have asked me to do assignment 3, so you have to listen to what I'm asking you and respond. Which one of these you would like me to do? 4 to 6? Okay. I'll start with 4 to 6, then we can do the remaining ones also. Okay, can you see my blank screen? I think you can see my blank screen, right? I'm going to write on the board, kind of digital board here, like I've done in all the lectures. Okay. I need to see the assignment somewhere. Give me a few minutes. I had logged in here. Okay, let's see. Actually, let's read the assignment here first. I will write, I will just look at what this is. Okay, let's read the assignment together and then I will go to the other writing screen. Okay, suppose in a network, host A is sending packets to host B over network path made of 2 links L1 L2. ये इस पे दूसरा बोर्ड आ सकता है क्या? और इस पे ये पढ़े ये नहीं होगा? अच्छा ठीक है, I'll manage. Okay, this is how I'll manage. Okay, I'm just going to write some essential points here, and then we will start solving it. Okay. So suppose in a network, host A is sending packets to host B over a network made of two links. In fact, I'll just copy paste this thing here. All right. So yeah, I'm going to go to this now. Okay. Suppose in a network host, yeah. So this is the host A, and we are sending packets over link 1 and link 2 to host B, right? And packets arrive at link L1 and then go to link L2, then to B. Assume infinite buffers at both links. That packet arrival rate lambda be equal to 15 packets per second, link bandwidths B1 equal to 112 packets per second, and so on. So let me first of all explain this scenario to you all. In terms of networking, what this is like, imagine there is a laptop or a computer, okay, and it is connected over some link. When we say made of two links, means actually there will be one router in the middle. Okay, these are sort of prerequisites about networking that were expected to be known. So this is L1, this is a router, and this is L2, and this is going to B. This is A, this is B. Okay, and see if I can. Yeah, there are packets basically being generated in this computer, some file or something, and they're going here, and the packet arrival. So here the packets are arriving at rate lambda, which is equal to 15 packets per second. Packets per second. Okay, and what is the link bandwidth B1 is equal to? So this L1 will have some bandwidth, right? This computer is connected. This computer is connected to this router. Let's call this router R over by some wire, let's say, and the wire is 112 kbps. Okay, these numbers are not very realistic for today's bandwidths. It was just to make your calculation easier. Today's typical bandwidths are gigabits and whatnot, but just for the sake of calculation, this number is being given here. And then B2 is 240 kbps. Sorry, 240 kbps. Okay, so now where are we? Assume packet size is 1000 bytes. So let's call packet size as L, let's say, and that is 1000 bytes. Typically, we show it by capital B like that. Answer the following questions. So I guess it asks for, let me check what it asks for. Throughput and utilization of L1 and utilization of L2, right? Yeah. Okay. So best thing is, since the arrival rate is given as packet in the units of packets per second, it's best to convert this bandwidth into a rate which is in packets per second. Okay, so I hope everybody understood the queuing system here, right? What is the resource here? Anybody wants to answer to me? What is the resource? See, we had in very first lecture we had done, right? What are the resource and what are the customers? What is the resource? What is the first resource? Anybody here? Nalini, Arnab, Manish, Akshit. What is the resource? You can type and tell what is the resource. Don't be afraid of a wrong answer or something. Just say whatever. Nothing is wrong. Okay, first resource is this first link, right? The link itself is a uh, shared resource, right? It's the packets are going to come at some rate, and the link has some capacity. Yeah, bandwidth is a number. Okay, bandwidth is a number that describes the resource, is a quantity that describes the resource. The resource is a thing, right? Resource was the CPU or the printer or the person and something. So the resource is the link, and yes, the link has a bandwidth. Yeah, processor, server are the resource. In this case, if I'm talking about the links, then I'm obviously ignoring the other things, right? What I'm talking about here is the links. I'm giving you information about the links. So I'm focusing on the link resource. Yes, processor and so on are also a resource, but we are not kind of focusing on those resources right now. I'm just worried about the link and I want to model the links. So I've given you the link bandwidth and I've given you the packets per second arrival rate. And I have given you the bandwidth in terms of bits per second and the packet size in terms of bytes. So you have to convert that, right? This basically, this is not the subject of this course. By the way, in computer networks, you are kind of expected to have done that, if this is, let's say, some source and this is some destination, okay, and there are packets that go on this, okay. So if the bandwidth is say b1, yeah, so bandwidth is b1, right, bits per second, let's just say bits per second, and packet length is L, also bits, then the time taken for the transmission of this packet, meaning this packet needs to go on this line and start transmitting, that time is L by B1. So this is bits and this is bits per second. So this becomes a seconds unit. So that is the standard formula from networking, that if there is a certain packet size and you know the bandwidth, then packet size divided by bandwidth is the time taken to send that packet. So this is our tau. This is kind of, in our terminology, this is the tau. And we need to just find the tau. And the first, basically it's the queuing system version of this is, it's a tandem queue. Basically it's a tandem queuing question. This is lambda, right? It's a tandem queuing function question. This queuing system is corresponding to this first link, and this next queuing system is corresponding to this second link, right? After the packets cross this link, there is a router, but if you're not told anything about the router, means we are not assuming any bottleneck in the router. Maybe the router is very fast and the links are the bottleneck, so we are focusing on the links. So these packets may form a queue here depending on how they come. They may form a queue here and they will form a queue here, and the resource is this link and here is this resource. So that's the two queuing systems. So basically this is a tandem queuing system question. Tandem queuing system. And you had done a whole lecture on tandem queuing system, right? Where the first queuing will have some service time tau1, and the second will have some service time tau2, and based on how the lambda is with respect to this tau1, tau2 and all of that, some interesting things can happen. Very, very different based on which of these links is the bottleneck. The utilizations of the links can be different, right? So let's do the calculation. First of all, let's find the bandwidth B1 in terms of packets per second. Okay, so if 112 kilobits per second, so let's try to find tau1. That is going to be, the packet size is 1000 bytes. So convert it into bits, 8 bits, and the bandwidth is 112 kilobits per second. So we can just use 1000 for kilo. Okay, so 112 multiplied by 1000 bits per second. Okay, so that's 8000 by 112. How much is that? One to multiply by 1000 also, but we can just convert this to milliseconds. So I'm actually just going to divide 8000 by 112. and we get around 71.42 packets per second as the rate. Okay. Sorry, not rate. What am I saying? 71.42. This is divided by 1000 seconds is the time. Right? Tau 1 is the time we are trying to find. What is the time to send one packet? Right? Packet size is 8000 bits. The capacity of the link is to send 112 multiplied by 1000 bits per second. So the time required to send a packet is going to be how much times is 8000 take and divide. It's sort of a distance divided by speed thing, right? So this is the length of the packet divided by the speed of the link. So 71.42 divided by 1000 will be the seconds, and that means it will be 71.42 milliseconds. Okay. So this is the tau 1, and what is the rate? We can find the rate by doing 1 by tau 1, right? So what is the mu 1? That is actually 112 multiplied by 1000 divided by 8000. So this is 14 packets per second. Okay. So the rate of the first link is 14 packets per second. There is the next page here. Let me do this again. Right. So I have the queuing system here. Lambda is equal to 15 packets per second. This is L1. This is L2. Okay. B1 is equal to 112 kbps. B2 is 240 kbps. Packet size L is equal to 1000 bytes. So tau 1 is going to be L by B1. We can also directly just find mu 1, which is B1 by L, which is 112 multiplied by 1000 bits per second divided by 1000 multiplied by 8 bits, right? And by when we divide it by the size of the packet, we are going to get how many packets per second the link can send, or PPS. So this is 14. Okay. So this is clearly telling us about what's going to happen at this first link, right? So lambda is 15 and mu 1 is 14. Right? Let's find out what is mu 2 also. Okay. So tau 2 is going to be L by B2, and mu 2 is going to be mu 2 by B2 by L. B2 is 240 kbps, so multiplied by 1000 bits per second divided by again 8000 bits. So this is equal to 40 packets per second, right? Sorry, 30. 30. 8 3s are 24. Now what am I doing with my math correct? 8 1 8, 8, yeah, 8 3s are 24. And yeah, this is fine. Okay. So now remember your tandem queuing methods. I hope you have made notes. We are actually also, there was some issue with the slides, so it was a little delayed in sharing. They're ready now, so we will share them. But from the tandem queuing system, do you remember what the first question here is? What will be the throughput, right? What was the question? What is the throughput of the whole path? Right? So throughput of the whole path is going to be 14. Why? Because here, even though the rate of arrival is 15, okay, even though the rate of arrival here is 15, the mu1 here is 14. So the output here can only be 14. Remember, throughput is equal to minimum of lambda and mu1. So minimum of lambda or mu1 here is 14. So that's all. Even though 15 packets per second come, this link can only carry 14 packets per second. So the throughput here is going to be 14. Okay. So if now 14 packets are coming per seconds are coming here, but mu2 is 40. So mu2 can, 14 is less than 40. So output here is going to be 14 packets per second. So what reaches B here, the destination, is 14 packets per second. Okay, so that explains the first answer. Second was, what is the link utilization of L1? Yeah, so this is easy, right? This is basically arrival rate was greater than capacity. So remember, your utilization is equal to minimum of 1.0 lambda divided by mu1. Here lambda is 15, mu1 is 14, so it's going to be greater than 1. So first link utilization is 1. And second link utilization will be, rho 2 will be just 14 by 40, 14 divided by 40. So that is what the answer must be. Yeah, 0.46. If you do 14 by 40, the answer will be something in between that. Okay. Let me check exactly what it is. Is it coming 0.46 to 47? Oh, sorry, not. Okay, I wrote it wrong here. It's 30. It was 30. Yeah, we calculated it at 30, right? 240 multiplied by 1000 by 8000 is 30. So mu2 is 30. So this is 14 by 30, which is basically 0.467. That is what the range is. Okay. Any questions about this? Okay, those who wanted me to work out problems, please ask some follow-up questions. Is it clear? Is there still any doubt? I can just repeat. This is pretty much according to the formulae and everything. Question 7 to 10 should be more straightforward, right? Okay, you guys have to give me some feedback so that I know what to do. The whole point of live session is that it cannot be a monologue. Otherwise, I would just record a lecture. Okay, I know that the interactivity is okay. Arnab, how to optimize the values? Okay, good. Thanks, Nagini. Arnab, can you expand on that little? What do you mean? Which values do you want to optimize? You mean how to optimize response time or something? How to reduce response time? To put values. I'm still not sure what is in your mind. If you could give an example, just type a little longer. What is the what is weighing on your mind? If I understand, then I can answer. I know it's a problem that you cannot speak, but try to type. How to increase? You what? I mean, how do we have higher throughput? Is that what you are asking? So, I mean, I can just keep saying something until you type your more longer question. So, one of the things, of course, I mean, queuing systems, we just analyze systems, but really what the people who are, let's say, now in this example, there is a link and the bandwidth and all of that given. This situation that is happening that the packet arrival rate is 15 packets per second, but the link bandwidth is only 14 packets per second. This is not a good situation. Maybe that is what Arnab means, that more work is coming to the link and the link is slow. So how can we make it faster? So in some sense, actually, directly, this is not the topic of this course. We just kind of analyze whatever is there. But this has to give feedback to the engineers as to how to. So one thing here could be that you need two links of that. If you cannot have a better link, you should have two links. Make it a GG2 server. So then maybe you can divide the traffic between the two links, and now total capacity of the link will be 28 packets per second. If 15 packets per second are coming, you will be able to carry it. So how to optimize and increase throughput? You have two, in our sort of simplistic way, you have two ways. You either reduce T1, which means mu1 will increase. Somehow, if this link was of some old type, then you should put a new, high bandwidth link. Or you have to put more links. You to just put, so basically total capacity of anything is, the overall view. We know from our theory is that C mu is what we can do, what any server can do. So the way to increase the capacity is either increase C or increase mu. Increase mu means tau should be less, means the increase capacity by adding more resources or making each server faster. So somehow if it is in your hands to reduce this tau per request processing time, then do that. If you can't do that, if it's like very difficult to make any one thing fast, then you need to have multiple of the resources. You just, there is no alternative. You just have to increase your C. There is one more tool, which queuing systems can kind of, it comes under the purview of queuing systems, and that is a scheduling discipline. So sometimes your effective capacity of your system and effective performance of your system is decided by your scheduling discipline. So you can have a, for example, if you have priorities in your in your customers and you want to give high priority to a certain customer, low priority to another customer, then your scheduling discipline should be such that the high priority customers are served first. If you have an interactive workload, then you should go with round robin. If you have a batched workload and it's sort of to be done and you know the job processing times, everybody knows that you should go with shortest job first, right? If you want to improve the average and the response time of any one customer doesn't matter, you're just supposed to, let's say you get a workload that you have to do overnight, okay? It doesn't matter then which request came first, which request came later. You might as well just do it in a way that the whole thing gets done fast, and that will be and that the average response time rather than the overall, so that this like short job is not stuck behind the long job. It will get done, faster. So that sort of you can have various scheduling disciplines which will optimize, as you say, shortest job first optimizes response times for short jobs. Okay, so there are all those ways that one can use. Other than that, if the server is a code, then your code should be fast. You should optimize your code. Those sort of things are outside of scope of this course. But yeah, the tau, to reduce the tau, sometimes if it is actually an execution of a request like web server or something, you have to write faster code, so that better code, so that it will be faster. These are all the ways to improve throughput. You should also size your buffers correctly. They should not be too long. If buffers are very big, then requests time out. They will sit in the queue and they will time out. If buffer is too small, then the request will just get dropped very easily. So buffer sizing exact to the exact size is a very important thing that actually queuing systems can tell you about. It's a little advanced. We didn't do that. We didn't do loss probability and all of that. It's a little advanced, but you can calculate loss probabilities and you can help in deciding, use loss probabilities to decide what should a buffer size be. And that can optimize your throughput. Any other question? Any of the old assignments, assignment 4, I can't yet work out because it's due in 2 days. But any of the previous assignments, anything else you want me to work out? Is this all okay? Any of these answers, do you need any explanation? Anybody needs any explanation? This is an interesting question. I hope you got it. Please ask your questions. Our time is running out. They have a slot. My slot will get over at 4 o'clock. Is there any question on the week 4 lectures? Okay, should we wrap up? Okay, I'll just wait till the end of the session for any questions. Otherwise, we'll wrap up. Any other broader questions? May not be to do with the working out of assignments, just any general questions. It is open session, live session. You can really just ask me anything you want. Okay, we should probably wrap up then. Thank you, everyone. We will share the worked out solutions in like written form for a few more assignment questions, the slightly advanced one. Please post on the discussion forum, what questions you want. That Gmail that is shared on the thing, that Gmail, you can also just send individual questions if you are a little shy about writing on the like posting on the group. I think you can just write to that email also. time between requests is exponential with the mean time equal to 8 milliseconds. Time to process is exponential with what is the average response time? Average response time, if you remember, is not a question one can answer that easily. It's one of the questions that keeps maintains open, remains open till the end until we can either get the queue length, right? So actually, average response time is not easy to answer unless I know the distributions, for example. Oh, okay, so this is MM. I mean, I need to know a few more things. If it is infinite buffer, then I can do MM1 and you have the MM1 formula, which is tau divided by 1 minus rho. So I can tell you here. Let me again share my screen. Okay, you can see my screen, right? So this is basically 1 by lambda is 8 milliseconds, and interarrival time is, you're saying it's exponential, right? And 1 by mu is 5 milliseconds, and average and service time is also, you're saying, is exponential, which means this is an, and let's assume single server. If we are going to assume single server, if we assume single server and we assume infinite buffer, then this is basically an M1 queue. Okay, and where the tau is 5 milliseconds and lambda is 1 by 8 requests per millisecond. So rho will be lambda tau, that is 5 by 8, that is a rho. And response time, if you remember, for MM1Q is actually tau divided by 1 minus rho. So this is 5 divided by minus 5 by 8 is 8 6 are 48, 28, 2 are 16, I think 0.625, right? Yeah. So this is 1 minus 0.625. So that is the with these assumptions you can give the answer, but without that you cannot give the answer. Not that easily. So if it is not exponential, so the only thing here is it not C? I mean, is it not 1 or is it not infinite buffer? In which case, if this is some finite, then it will be an MCK model. And actually, there is a formula to do this. We didn't learn it in this course, but you can actually answer this question. If they are both exponential, then with a little bit of more math, you can answer. You have a more complicated formula for the response time, but it exists. Okay, you have to look at advanced queuing theory books, and you will get that. Okay, but in the absence of anything, we can always make the assumption that it is single server infinite buffer and get some estimate, some idea. Any other examples of modern networks apart from discussed in software? I mean, even in 5G, I had told actually I forgot to share that paper. So I will share the paper. In 5G core also, there is a lot of elements. Finally, no matter how modern something gets, there are processors and there are, wires that are going to carry bits. That doesn't change. It's just the scenario changes slightly. Uh, there is software defined networks in that the links and the bandwidths, those continue to be the same. That will not change. There will be different bottlenecks in terms of entities in the network that control the network elements. Software defined networks have a different design where you are the packets are going through switches where there are different basically it's a little more, the whole routing and everything is defined by software, not so much configured into the router. So there'll be other elements, there'll be some other servers that will become the bottleneck, and that it's the same queuing systems that can apply there. So there are lots of examples. Wi-Fi itself is a very complicated queuing system, and there are some, there's some very advanced paper on treating the Wi-Fi as a queue, and it's not very easy. It doesn't fit into this MMC and GGCK and all of that easily. So a little complicated mathematics is required, but it is still a queuing system with a distributed, there isn't a single place where all the packets for it queue. If you have like 20 laptops all on wireless in one machine, it's the same wireless resource channel that is being used by all these laptops, and that is a queuing system, but it's a complicated queuing system. So these are there. There are examples, but as is with modern systems, things get a little complicated. So in an introductory course, we like to keep things simple, and the examples are also simple. That is why, but yeah, if you do this course well, then you should learn more about this subject and apply the same theory to more advanced systems. Modern software systems, there is nothing that makes a software system not a queuing system. It's software is software. It's some server, some multi-threaded server will be running somewhere, and it's a server. Right? How does it change? By modern, what is the trait you want to model? If you tell me that, then I can respond. So Nginx server is a web server. Of course, it's a queuing system. It's a multi-threaded queuing system. There are proxy servers. They are queuing systems. Only thing here, of course, we have a notion of a resource and customers. One of the modern systems that cannot be modeled easily with this traditional queuing networks is peer-to-peer systems, because there is no one clear client and one clear server. So peer-to-peer systems are very interesting, and they have to be modeled using not this sort of textbook theory, but some innovative new approaches. They can also be based in queuing systems, but then that becomes a little bit research work as to how does one model peer-to-peer networks, peer-to-peer systems. Because they are both clients of each other and servers. One is a client of the other and the server, and you play both roles. So it's not so clear. So that is one example of modern software system, which is actually not so easy to model directly by the textbook material that you've learned. You can still do it, but it will require some high level, more advanced material. Other software systems, we didn't learn very advanced stuff. Was things like layered systems where one, let's say the web server will call the database server, let's say the web's front end, there will be some front end server that calls a middleware server, the middleware server calls the next server, the third level server calls the fourth server. These are multi-tier systems. There also you can use queuing systems, but it gets complicated, and we didn't do it at our, again, our sort of introductory course level, we didn't do it, but advanced, you can look at something called layered queuing networks. So layered queues are used for that. That's also an interesting thing. Model view controller is a software coding paradigm. How it turns into resources and customers will not, you'll have to think about how finally it is just a Django Python server, and you'll have to think more about how many threads does that server have, what is the queue size, and functionally what is it doing. Is it executing model code or views code or controller code will not matter so much. These are software layers, these are not necessarily resource layers. You have to be very careful about whether you're talking about software or you're really moving between resources. So the resource here will simply be the Django Python server with multiple threads. So that will come back to just a multi-threaded server. Yeah, it's a good question. Does model view controller, is that like a tandem queuing network? No, it's not. You have to, the software view of something and the systems view of something is very different, and it's a very good exercise. It's a very good question. If you are going to work more on this, then it will be very interesting. How does one model a Django Python server using queuing systems? It's easy, it's not a big deal. The model view control model in fact comes at the end, right? And the model part of it will result in the database call. So it will actually turns out to be a multi-tier, the example that I was giving. In fact, this is exactly what I had in mind. Front end, there is web server. Then we have the Django Python server, typically WSGI gateway, if you know all those things. And then there is a database server. So this is typically 3-layered architecture, and what we model here is all those 3 layers. What impact will 5G performance have on backhaul networks? So I'm being told to wrap up. Okay, you guys, I was waiting for so long. Now all your questions are coming. These are all interesting questions. But I will answer the last question, and I'm being told, there'll be somebody else's slot, so I have to wrap up. So 5G performance has a huge impact. I would encourage you to read papers by my colleague Maithili Buttukuru. She is writing a lot about 5G, and there is a lot of, Arnab, if you're interested in 5G, you should write to Professor Maithili Buttukuru. She might be hiring interns or taking students or whatever. You're most welcome to find out more about what's happening. 5G, what is in short, I will say there are a lot of software components in the 5G core, and they are all being implemented on commodity systems. And there is a lot of work required in optimizing the network stack, making it work with the things like programmable switches. There are issues like offloading. Where do you do the processing? Do you do it in the switch, or do you do it in the controller, server, the control plane server? So what impact will it will have? It's supposed to make things very fast, but you have to work at making it fast. Yeah. So the professor is Maithili Buttukuru. Okay. So you can Google her work and look at her website and so on, and you'll find a lot of work on 5G on her website, I hope. Okay, thank you very much for the very nice questions towards the end. I don't know whether I can do one more live session, but we have to wrap up today's. Okay, thank you very much.